what we're going through today here, it's called linear approximation. A linear approximation basically is a method where we are going to turn a fairly complex equation. This one's actually fairly simple for the type of equations we can use this with, because we don't want to make the first one too complicated. But where we can start with a very complex equation even, and boil it down to something that lets us find an estimate for certain values much quicker and easier than we could without it. Now, the whole idea behind this process actually goes back to what happens when we look at the graph. As if I take a look at the graph here, this is the graph of my cube root equation. You notice it's been shifted left 1 because of the 1 that's inside the parentheses there. And it's telling us that we're working with the point where a equals 0. And so it tells us that we're working with that point right there. The reason why we're choosing to work with a being 0, basically it's because the distance from my starting point, my normal starting point, and this point is 1. And the two numbers I'm going to be estimating are going to be close to 1, the 0.95 and the 1.1. But we'll get more into that as we go on. Now the method can work because we're going to be looking to see what happens when we get really close to that point. Notice if I zoom in on that section of the graph, my graph here, it almost looks like it's a line, right? And so if I want to know, for instance, what is this value here? Well, I might as well just figure out, okay, what's the value on the line that goes through there? And that's going to be really, really close. So the first step of this linearization process is we find the equation of the tangent line at that point. All right? The nice thing about that is we've done that lots. We know how to find the equation of the tangent line. We're going to find the derivative, because that'll let us find the slope, and then we'll plug in our x, y, and our slope to find the y-intercept. Okay, so let's go ahead and do that process here. I have g of x equals the cube root of 1 plus x. What should I do first in order to find this derivative? Yeah, let's rewrite it. Because the cube roots, they can be a bit of a pain. All those roots can be a pain. We instead write it as an exponent. So this becomes 1 plus x to the power of 1/3. Having done that, you now can go ahead and find the derivative. So now we're going to figure out what is g prime of x. So to find our derivative, I'm first going to use power rule with that 1/3. So I go 1/3, stuff inside the parentheses stays the same, 1 plus x, and then I subtract 1 from the original exponent, so that gives me a negative 2/3. But because it wasn't just an x inside the parentheses, technically I have to be using chain rule here. So I did the derivative of the outer function right there. Now I multiply that by the derivative of the inner function. That's the 1 plus x. Well, in this case it's almost a little silly. Because what is the derivative of 1 plus x? 1. And so I'm multiplying it by 1. Okay, I'm putting it in there just because I want to remind you that yes, you still have to use chain rule because it won't always be 1. But yeah, that's hardly going to change anything. Alright, now I can actually proceed from here with it written in this form, but I do want to remind us that we can clean that up a little bit. So I'm going to go ahead and clean that up just to make it a little easier to look at here. So I know I'm going to have a fraction because I have that 1/3. The only thing that's going to be left on the top is the 1. The 3 is on the bottom. And that negative 2/3 power, that gives me the cube root of 1 plus x squared. Now a little detail about that squared. That can either be inside the cube root or it can be outside the square root. Either way, it gives you the same thing. But again, I don't have to go through that process strictly speaking here because my next step is I want to figure out what is the slope at this particular x value. Now what is the x value I'm working with in this problem again? It is 0. At the start of the problem it told us that we're using the value a equals 0. A equals is basically saying, okay, this is our temporary x value. It's the one that we're using kind of as our center of estimating. So I'm going to plug in 0 for x. So let's go ahead and plug that 0 in for x in our function there. and see what that gives us. And so when we do that, you should end up finding that in this case, it happens to just equal 1/3. Nice and simple. That's usually one of the nice things about plugging 0 into an equation is it gives you something that's fairly simple as a result. It won't always be 0. It always goes back to just in the original question, what was the a value that we were working with. All right, so I know that g prime of 0 equals 1/3. That means I know that the slope at the point that I'm looking for is 1/3. I can now go and start dealing with writing the linear equation through that point. So y equals mx, so that's going to be 1/3 x plus b. All right, now I plugged in the 1/3 because that was my slope through my point. And I know what the x is. We just talked about that. The x has to be 0. And we're going to solve for b. But what is y? Well, you actually might have already known because I put the graph up. But on these, if you don't know what y is because it wasn't given in the original problem, then let's find out. Because the y value is just g of 0. We just plug our x value back into the original equation. It'll tell us what the y value is. So if I do g of 0, not g prime, but g of 0, I end up finding that g of 0 is 1, because the cube root of 1 is 1. And so it's going to be 1 equals 1/3 times 0 plus b. Having gotten to that point, we go ahead and solve it for b. Conveniently enough, the 1/3 times 0 becomes 0. So just 1 equals b. And so then we have our equation. Y equals 1/3 x plus 1. Now there is one final thing that I'm going to throw in here. One last step. When we're talking about the linearization, this is actually a very specific type of function for a specific kind of use. And so because of that, we actually have a special way to represent the linearized equation. Instead of calling it y equals, we are going to call this capital L of x equals the 1/3 x plus 1. When we see capital L of x, that's telling me that it is the linearization, or in other words, that's a fancy term for just saying the equation of the tangent line through that particular point. But unique processes come with their own unique language, so what are you going to do? Having gotten this far, we're not done. This is like the halfway step. So we can kind of see now what's happening with this if I take a look back at the graph. So now I have both graphs overlapping. I have the line there, and you can see that if I'm looking just in this little area, the values that are on that line are very close to the values that are on that curve, right? In fact, I can look even closer. This is what that looks like if I zoom in. They're really, really close. Now, of course, the further out we get, the less accurate they are. But the closer in we get, the more accurate they are. And so this is really an estimation technique that is going to have some error to it, but the closer you can actually be to the original values, the better. All right, now we're going to be using this to approximate these two values. Now, let's talk about what x really means for each of those. If I'm going to be approximating the cube root of 0.95 using this equation, I'm not just going to be plugging 0.95 in for x. Because notice, if I plug 0.95 in for x up here, that'd give me 1.95. I'd be estimating the cube root of 1.95 there. That's not what I want. I want to estimate the cube root of 0.95. So if I want this 1 plus x to equal 0.95, what would x have to be? Negative 0.05. Absolutely. And so for this one then, I'm going to be using x equals a negative 0.05. Graphically speaking, what that means is basically I'm going to be looking at a point that's right over here somewhere. Just kind of helping to visualize when it comes to the graph. Okay, what about the 1.1. 1 plus what would be 1.1? 0.1. So that tells me for this one it's got to be x equals 0.1. So for that one then, that means we're going to be looking at the value that's somewhere over here. Again, visualizing that on the graph can help, because what we're really doing is we're seeing that, notice that the point on the curve and the point on the line there are extraordinarily close. So whatever estimate we come up with here is going to be pretty close to the actual value. We now have enough information to go ahead and finish off this problem and do our two estimates. So I figured out my linearized equation. That's the linearization. And I figured out that for the first one, for the 0.95 here, I'm going to have to figure out what is L of a negative 0.05. Again, because I'm saying what do I plug in for x in order to make that be that number. All right, so we plug that in. So we do 1/3 times a negative 0.05 plus 1. All right, when you did that, if you got your answer as a decimal, you'd be getting 0.983 repeating. The 3 is repeating there. Or you could also give it as a fraction, because you'll notice that this negative 0.05, that's just a negative 1/20th. So I could actually use that to do the math mentally, and that would give you an answer of 59/60ths. Either answer would be fine there. All right. Repeat the process now for the 1.1. So remember that you're actually finding out what the value of L of 0.1 is. Make sure that you actually plugged in 0.1, not 1.1. And so if you do that math, if you did it as a decimal, you'd be getting an answer of 1.03 repeating. Or as a fraction, again, the 0.1, that's 1/10. So 1/3 times 1/10 is a 30th. So that would be 1 1/30th. Or, if you prefer, 31/30ths. Now, inevitably at this point, the question arises, why did we do that? If we're going to use our calculators to get this decimal here, why didn't we just get our calculators out and do the cube root of 1.1? Well, we could have. But again, we're starting with a simpler example here so that you can then apply the process to a much more complex example.